sea, darling, on deep, deep blue sea, deep blue sea.
Okay, we're on to section 4.2. So the rest of this chapter we're going to be looking at exponential functions and logarithmic functions. So here we go with exponential functions. So what are those? Well, an exponential function is a function that has the form f of x equals a times b to the x, where a cannot equal 0, b is greater than 0, and b does not equal 1. Wow, that's a lot of restrictions. And we're actually going to talk about those restrictions later on. But for now, let's focus in on this bit of the equation, f of x equals a times b to the x. And what we're going to do today is we're going to graph a bunch of stuff. And what we're going to graph is, when you're graphing, instead of thinking of f of x, remember f of x is really kind of the same as y. So we're going to be graphing y equals a times b to the x. And for today's lesson, what we're always going to make a is 1. A is just going to be 1. So in other words, since it's 1 times something, the 1 doesn't really change anything. So we're going to be graphing y equals b to the x. That's what we're going to do today. So if you look at these two, we're going to put these two functions in this first graph. You can see the b value is 2, the b value is 3, the b value is a half, the b value is a quarter. And the a value, if you want to see it, there's an a value right here of 1, there's an a value right here of 1, there's an a value right here of 1, and there's an a value right there of 1. Those are brackets I'm putting after. Okay, so just to give us an introduction today, the a value will always be 1, but this is really the form of an exponential functions. Okay, let's start by graphing y equals 2 to the x power. So this is kind of strange because we have our x value, the input value, in the exponent position. We've probably never done anything like this before. So when you're learning something new and you're graphing, you don't know where to start. So the method to graph things you really don't know what they look like is you use a table of values. So that's what we're going to do here. So y equals 2 to the x. Let me just rewrite that down here. And I'll set up a little xy table, t-table. And it's good to pick some positive numbers, 0, and also some negative numbers. It doesn't always work, but that's a pretty safe bet. This is going to be useful to do this. So all you do is you plug these x values into the exponent position. So you end up with 2 cubed, right? You put a 3 right there. 2 cubed. What's that equal? 8. 2 times 2 times 2 is 8. 2 squared, that's 4. 2 to the first power, that's 2. Now be careful here. 2 to the 0 power. We did this the last couple days. 2 to the 0 power is 1. Anything to the 0 power is 1. Okay. This is something else we did a couple of days ago. 2 to the negative 1. I'll just write that over here temporarily. 2 to the negative 1. What's this negative here? That's a flippin' negative. So it's going to become 1 over 2 to the 1 power, which is just 1 over 2. So this is 1 over 2. I'll put it like that. I hate writing my fractions like that with the diagonal, but I'll do it. 2 to the negative 2. Well, if this was negative 2, you'd do the flippin' negative, and then you would square this. It'd become 2 squared. You get 1 over 4. And this, boy, that's terrible writing. That's 1 over 4. And if you put a negative 3 in there, this would become a cubed. You get 1 over 8. You can see there's kind of a pattern here. 8, 4, 2, 1, 8, 4, 2, 1. Anyway, let's graph that. So we have the point 3, 8, and then 2, 4. Let's do a couple. 3, 8, and then 2, 4. And the next 2 points are 1, 2, and 0, 1. So 1, 2 is here, and 0, 1 is right there. Okay, negative 1 and 1/2 is right here, and then negative 2 was at a quarter, so it's even lower, and negative 3 was at an 1/8, so it's even lower. I can't really do it. So anyway, if you look, this curve on this side, it just keeps getting bigger and bigger and bigger. It goes like this, and it keeps going forever. Now, what's happening down here, though? If you think about it, it's getting closer, and it's getting smaller and smaller and smaller and smaller. What if you had a really small number, like to the negative 10? Say you put negative 10 in here. Well, then this would be 1 over 2 to the 10th. 2 to the 10th is some giant number, so you'd have 1 over a giant number. Well, 1 over a giant number is a really, really small number. What if you made it even smaller number, like negative 100? It'd get even. What I'm trying to point to here, do you see you'll never actually get to 0? It's going to get closer and closer and closer and closer and closer and closer and closer, but it's never going to actually get 0. So it's going to be very hard to draw, but I'm going to try to draw this so it's getting closer and closer and closer. Basically, I'm just running it along the line there, okay? That graph right there is y equals 2 to the x. Okay, what if we change things just a little bit? What if we make it y equals 3 to the x? I mean, it should look similar, shouldn't it? But let's see exactly how it looks. And let's do this a little bit quicker this time. Y equals 3 to the x. So again, x, y, 3, 2, 1, 0, -1, -2, -3. 3 cubed, put 3 in there, 3 cubed, that's 27. 3 squared, if I put a 2 in there, 3 squared, that's 9. 3 to the 1 is just 3. 3 to the 0, well, anything to the 0 power is 1. 3 to the -1. 3 to the -1 means that's a flipping negative. It becomes 1 over 3 to the first power. So just 1 over 3. 3 to the -2. Well, when you flip it, there'll still be a 2 here, so now it's 1 over 9. And 3 to the -3. When you flip it, it'll be 3 cubed. You get 1 over 27. So let's graph these in blue. 327 we can't graph. It's off the graph. So 2, 9, and 1, 3 are our first points. So we can graph 2, 9, and then 1, 3. And then I know the next one's 0, 1. I remember that. That's interesting. Then we have -1, 1/3. So -1, and it's already below. This was a half here, so it has to be below because it's only at a third. And then 1/9, so it's even below there, but it's hard to see. So again, on this side, it's going up like this. But you see what happens as you put a bigger number into this position right here, the B position, right? It gets steeper. And then this kind of gets closer and closer and closer. It looks like it just runs along the bottom. There we go. I like my graphs. I think I did a good job here. Y equals 3 to the x. Both of these graphs, by the way, these are both called increasing functions. And I hope that's somewhat self-explanatory why they're increasing functions, because as you move from left to right, they get bigger and bigger and bigger and bigger and bigger. Increasing functions. As you put bigger numbers into this position right here, you get bigger output values too. Okay, so what these two graphs have in common is that the b values, the 2 and the 3, these are greater than 1, right? Remember, the b value cannot be 1, so we're kind of interested in what happens when it's greater than 1. The b value has to be greater than 0, but what about b values that are between 0 and 1? How we write that is 0 is less than b is less than 1. So that's what these ones are, right? 1/2 is between 0 and 1. 1/4 is between 0 and 1. What happens there? Do we get this same shape? Well, if I'm asking the question, you can probably bet the answer is no, you get something different. So let's do the same thing. Let's graph this. Y equals 1/2 to the x power. So I will write that down here. Y equals 1/2 to the x power. I have to put it in brackets, otherwise it would just be 1 to the x over 2. So, okay, we put our table and we'll use our same values: 3, 2, 1, 0, -1, -2, -3. So if I put a 3 in here, I get 1/2 cubed. That's 1/2 times 1/2 times 1/2. That equals 1/8. If I put a 2 in here, I get 1/2 squared. That's 1/2 times 1/2. It's a quarter. If I put 1 in here, it just stays the same, 1/2. If I put 0 in here, anything to the 0 power equals 1. If I put -1 in there, all right, let's write it down. 1/2 to the -1. Well, that's a flippin' negative. So it now becomes 2 over 1, or just 2. So this is 2 right here. What if there's a -2 here? Well, then you would flip it and get 2, but you'd also have it now that the exponent would become a +2, so you'd get 4. And what if you had -3 here? Well, the flippin' negative would flip this, so it'd become 2, and then it'd be a 3 there, so you'd get 8. Compare this, what we just did, to this over here. I think you're going to see something. 8, 4, 2, 1, 1/2, 1/4, 1/8. 8, 4, 2, 1, 1/2, 1/4, 1/8. It's the same thing, except it's going in a different direction. So let's graph this. The first point is 3 and 1/8, so it's going to be very low. 2 and 1/4. I'm doing the best I can. I know this is not perfect. 1 and 1/2. 0 and 1. -1 and 2. Then we've got -2, 4 and -3, 8. -2, 4 and -3, 8. And there you go. This is the first graph. It goes up and up and up and up, and here it goes down, 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 but it gets closer and closer and closer and closer. It never reaches the x-axis. This is y equals 1/2 to the x power. So you saw that pattern down here in these two sets of numbers. How does that play out in the graphs? So we're comparing the red graph and the green graph. What do you notice? What I notice is they're really kind of exactly the same. There's just been a reflection. Where's the reflection? There's been a reflection with this graph and this graph. They're just reflections over which line? Reflections over the y-axis. If you were to put a mirror right on the y-axis here, this part of the red curve would then flip over to this part here, the green, and this part of the red curve down here would flip over here to the green. So the reflections. What would be the reflection of y equals 3 to the x? It would be if y equals 1/3 to the x. But just to mix it up a little bit, I made it y equals 1/4 to x, just to change it a little bit. So let's do that last one quickly to see what happens when we have a smaller, right, 1/4 smaller than 1/2. What happens when I put a smaller number into this b value here? What happens to the curve? Okay, y equals 1/4 to the x power. Not the most attractive color here. 3, 2, 1, 0, -1, -2, -3. Put 3 in there. That's a quarter times a quarter times a quarter. Whoa, that's big. Well, it's actually tiny. 1/64. Put 2 in there. A quarter times a quarter is 1/16. Put 1 in there. Just stays a quarter. Put 0 in there. Anything to the 0 power is 1. Put -1 in there. Well, it flips, and then it's going to be 4 to the +1, or just 4. Put -2 in there. It flips, so it becomes 4 squared, 16. Put -3 in there. It flips, you get 4 cubed, 64. Most of this is off the grid. We can only actually do 3 points. The first point is 1 1/4, which would be down here, would be lower, because this was at a half. Then 0, 1, that 0, 1 point, fascinating. And then -1, 4. So -1, 4. So you can see that it's steeper, this case, as the b value gets smaller, it gets steeper this time. And that's not, I was doing so well with my curves, I'm not too happy with that one. But hopefully you get a sense. Alright, I have a word down here at the bottom, an amusing word, asymptote. Did I talk about this before? An asymptote is an imaginary line that a curve gets closer and closer to, but never reaches. So what are the asymptotes in these graphs? The asymptotes are the x-axis, right here, right? The curves are getting closer and closer and closer to this dotted yellow line, but it never touches. I know it looks like they're touching, but they're not supposed to, and it never crosses. This is an imaginary line. It's not part of the graph, but you know, we can think of it being there and imagine those curves getting closer and closer and closer to it. So that's the asymptote right there. Okay, so there's some definite similarities with all these graphs here. So what we're going to do now is kind of summarize the similarities. First thing we're going to look at is the domain. So the domain of all of these curves, if you notice, they all go forever to the left, right? Even those ones are going forever to the left, and they all go forever to the right. So the domain of all of these is exactly the same. The domain is x is an element of the set of real numbers, or if you want, from -infinity to infinity. Okay, let's look at the range. So the range, it goes up forever, up forever, up. They all go up to infinity. How low do they go? Well, they don't even quite reach 0. They get really, really close to 0, but they don't reach it. And they certainly don't go lower than 0. All the y values are greater than 0. Not equal to, just greater than 0. Or if you want, you could put from 0 all the way up to infinity. This one, remember, you could have put -infinity to infinity. These are the same thing. These are the same thing. X-intercept. Where do these things cross the x-intercept? They don't. Remember, there's an asymptote there. It never reaches the x-intercept. So we'd say none. Okay, here's an interesting thing. The y-intercept. Where does it cross the y-axis? Well, right there, and right there, they all cross at the same point. They all cross at 1. The point is 0, 1 is the y-intercept. And the asymptote. What's the equation of the asymptote in all these cases? The equation of the asymptote, I know what you're going to say. You're going to say, well, the asymptote is the x-axis. That's true. That is the asymptote. What's the equation of that? What does every point on the x-axis have in common? They all have the same y value, believe it or not. What's the y value of every single point on that axis? The y value is 0. So that's the equation of the asymptote. Y equals 0. That's the equation of the x-axis. And boom, like magic, that occurs. End behaviors. What do I mean by end behaviors? I mean, which quadrants do they start and end in? All of these have their end points, like have the arrows and go on forever and ever and ever in this quadrant and this quadrant. this quadrant, and this quadrant. They never go down into these two quadrants. These are the third and fourth quadrants. So the end behaviors here are the second quadrant and the first quadrant, the second quadrant and the first quadrant. So we say from quadrant 2 to quadrant 1, which I don't really like because it makes it sound it starts in quadrant 2. It doesn't start anywhere, but the ends, even though there is no end, so that's also odd, the end of the graphs are in quadrant 2 and in quadrant 1. By the way, I forgot to say something in here. Do you see that these functions right here are decreasing functions? As the x value gets bigger and bigger and bigger, the functions get smaller and smaller and smaller. Okay, very quickly I want to talk about a special exponential function, which is y equals e to the x. Believe it or not, e is a number. I don't know if you've encountered that before. It's a very important number. It's an irrational number like pi is. So remember, irrational numbers are decimals that go on and on forever. They never stop. They never repeat. It's approximately equal to 2.718281828. But how long does this really go? It goes forever. It never repeats. So this is just approximate. It's called, I know you want to say Euler's number. It's Euler's number. It's my favorite mathematician. He's a Swiss mathematician, or he was. He was the kind of came up with this number. Some people say discovered, some people say invented, and some people say it wasn't him at all. It was a man named John Napier. But anyway, E is actually very, very important. It's used in finance a lot. We're actually going to see that in this course when we're looking at interest, compound interest. Biology, when you're looking at animal populations and stuff, definitely uses E, and computer sciences also does. So it's a very important number, and there's a cool way that you can get close approximations of E, and it's by using this formula. E equals 1 over 0 factorial, remember factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, I think you see the pattern, plus 1 over 4 factorial, plus dot dot dot, goes on forever. And you know, it never actually stops because it's an irrational number. So if you want to get more and more accurate representations of E, then you just keep doing more and more of this. For example, this first bit here, what's 0 factorial? Do you remember that? 0 factorial is 1. So 1 over 1 is just 1. Well, that's not very accurate. If the real answer is somewhere around 2.718, and I'm just saying this is equal to 1, that's not very accurate. So 1 plus, what's 1 factorial? It's also 1. So 1 over 1 is another 1, and 1 plus 1 is 2. That's still not very close because we said 2.7. Okay, what's 2 factorial? That's 2 times 1, which is 2, and 1 over 2 is a half. So we get 1 plus 1 is 2, plus a half is 2.5. We're getting closer. Okay, should we do one more? What's 3 factorial? That's 3 times 2 times 1, so that's 6, and 1 over 6. And if you add all those up, you get 2 and 2/3, or 2.66666. Oh, we're getting very close, and I'm going to stop there, but it's kind of cool and actually kind of blows my mind that this works. And the more of these you do, the closer and closer and closer it gets to this. And it doesn't take many more. Like if we did 1 or 2 more, you'd be very, very close to this. Pretty crazy that works. So let's show you how quickly we could get a sense of what this graph looks like. Let's make an x and y table. Let's just put 0 and 1 in there. So if x is 0, you'd have y equals e to the 0, and anything to the 0 power, even e to the 0 power, equals 1. If x is 1, then you'd have e to the first power, which is just e. And how much is e? Approximately 2.7. With those 2 points alone, you can get a really good sense of what the graph looks like. 0, 1 is here, and 1, 2.7 is about there. Is this an increasing or decreasing function? It's increasing. So remember, it's going to start low in the second quadrant, it's going to go up high in the first quadrant, so it's going to get closer and closer and closer to the x-axis there, and it's going to get higher and higher and higher here. And is that exact? No, it's not, but this is close enough to give us a sense of what this function right here looks like when you graph it. Okay, the last thing, again very quickly, I just want to look at why can't b be equal to 1, be equal to 0, and be less than 0. So remember, what we're looking at today is equations of the form y equals b to the x. And when we wrote this down at the start of the lesson, we said that b cannot be equal to 1. Why not? Well, that would give us an equation y equals 1 to the x. And if you did your table, x, y, 3, 2, 1, 1 to the third power is what? 1. 1 to the second power, 1. 1 to the first power, 1. 0 to 1 to the 0 power, 1. It's always going to be 1. So you're going to end up with a horizontal line like this. That's not exponential looking, does it? It doesn't look like the other curves we've done today. That's a linear. So it can't be equal to 1. Why can't it be equal to 0? Well, that would be y equals 0 to the x. What's 0 to the third power? 0. What's 0 to the second power? 0. What's 0 to the first power? 0, 0, 0. So you just have a horizontal line right on the x-axis. Again, that's not exponential. That doesn't work. And this last one's a little trickier. Why can't it be less than 0? So let's try something simple for that. Let's try y equals negative 1/2 to the x, and we'll do our x and y. Let's just start at 2 this time. 2, 1, 0, negative 1, negative 2. So if you put 2 in here, you get negative 1/2 squared. Negative 1/2 times another negative 1/2 equals positive 1/4. If you put 1 in here, it just stays the same, negative 1/2. If you put 0 in here, anything to the 0 power equals 1. If you put negative 1 in here, negative 1, all it does is flip it. So it doesn't change the signs or anything, it just flips it. So you end up with negative 2/1, or negative 2. If you put negative 2 in here, it flips it and squares it. So that'd be negative 2 squared. Negative 2 times negative 2 is 4. And if you graph that, you get 2 and 1/4, you get 1 and negative 1/2, you get 0 and 1, you get negative 1, negative 2, and you get negative 2, 4. And you can see you just kind of get this smattering of dots. Now, kind of looks like it might do something like this, but it doesn't. It doesn't work. So for these reasons, you cannot have b be equal to any of these things. One final thing I wanted to mention, some of these generalizations only apply to today's work. So remember, the exponential functions are all of this form, and today we said that a was always going to be equal to 1. And if that's the case, that a is equal to 1, all these things will be true. But some of these things will change if a is not equal to 1, and that's what we're going to do next day. This will change next day. X-intercept will always be the same. This will change next day, and this will change next day. So these three things, just to give you a heads up, are always the same for exponential functions of the form we're interested in. The domain's always going to be all real numbers. X-intercept's always going to be none, there is none of them, and the asymptote's always going to be the x-axis. But the range, the y-intercept, and the end behaviors can vary from what we've seen today. But for today's work, this is the pattern we saw. Okay, sorry for the very long video. Take care.
And it was brother that got drowned out in that deep